Hello everyone, my name is Anhong Guo. I'm a PhD candidate at Carnegie Mellon University Human-Computer Interaction Institute. Today I'm going to tell you about StateLens, a system that makes existing dynamic touchscreen devices such as public kiosks accessible to blind people without access to the underlying software or hardware of the devices themselves. This work was done with my collaborators Junhan, Mike Rivera, Frank Xu, and Jeff Bigham. So the world is full of physical interfaces that are inaccessible to blind people, from microwaves and information kiosks to thermostats and checkout terminals. Blind people cannot access these interfaces because the buttons are textually indistinguishable and the screens contain visual information that they cannot read. Making all of these interfaces accessible has been a long-standing challenge in accessibility, and many approaches have attempted to address this problem. So for static interfaces, my prior work on StateLens allows blind people to access them similar to using a screen reader. So when the user moves their finger on the interface, StateLens will provide real-time feedback of what is underneath their finger. And for home appliances, blind people often add tactile markings with the help of friends and family. My prior work on facade enables blind people to independently create 3D printed tactile overlays for static home appliances. However, enabling access to dynamic touchscreen devices is especially difficult because of three reasons. First, the visual interfaces change, so static tactile overlays won't work. And interactions occur over multiple different screens, therefore it's difficult for the user to search and navigate through each screen, and it's also challenging for the system to identify those screens. Furthermore, it is easy for the blind user to accidentally trigger touches while exploring the screen with their hand and finger, so they cannot freely touch and explore. It is just much harder to use dynamic touchscreens for blind users because you can't see where you're going and you can't touch anything to figure it out either. And to solve these problems, we introduced StateLens, a reverse engineering solution that makes existing dynamic touchscreens accessible. So here's the video of a blind user using StateLens to access a coffee machine mockup. So I want to mention that this setup with a head-mounted smartphone is definitely unwieldy, but in practice, it could be non-obtrusive and sleek with an integrated head-worn camera and headphones.
Stay, hot beverages, select strength, target, strong, move down, move down. Move down, and strong, press it, and strong, press it. Move up slowly, stay, hot beverages, place the right cup size and press go, target, go, move up, move up. Move up, move left slowly, no finger, and go, press it, and go, press it. And go, press it, stay, your drink is being prepared.
So as you can see in this video, the user can touch the interface without triggering accidental touches, then follow the interactive guidance, and then activate with a rock-down gesture at the desired button. StateLens have three major system components. First, it reconstructs the underlying state diagram from usage videos. And then using the state diagrams, blind users can specify tasks using a conversational agent and get step-by-step audio guidance to complete the task. And thirdly, StateLens provides users with risk-free exploration accessories for them to explore touchscreen interfaces without accidentally triggering touches. Now I will walk you through each component. First, StateLens reconstructs the underlying interface state diagram from usage videos. These videos can be collected through a variety of sources, such as through existing IoT cameras in the environment, from sighted volunteers, manufacturers, or by mining online repositories for demo and tutorial videos that people have been already taking. And then it uses computer vision techniques to detect the screen region in the video frames, and then uses a combination of SERV and OCR features to identify whether a frame is an existing state or a new state. And when an unseen state is detected continuously across multiple frames, StateLens is confident enough to register it as a new state. And then for this new state, StateLens will solicit additional information from the crowd, such as fine-tuning the screen area and its button labels, as well as using finger detection techniques to recognize the user interaction that triggered the transition. Using this hybrid crowd computer vision pipeline, StateLens can gradually build up the state diagram. For example, with this first video of a person using the coffee machine, StateLens is able to observe the transitions and add them to the diagram. Each image here shows a new state. The black arrow shows the state transition, and the red circles show the user interaction that triggered the transition between the two states. And the state diagram is more and more complete as videos are input into the system. And on the other hand, the completeness of the state diagram is also limited by the coverage of the collected videos. So this is related to research on pixel-based reverse engineering to extract GUI elements from screenshots or screencast videos. In comparison, StateLens extracts the structure of existing physical interfaces from the much noisier out-of-the-screen pixels, because it does not have access to the underlying software or hardware of the devices themselves. So now the state diagram is built. How do we use it to provide effective guidance to the user? Using a state diagram, StateLens first generates a conversational agent to guide the user to specify what they want to do. Using Google Dialogflow, the interaction traces in the state diagrams are mapped into intents, and the steps along the trace are mapped to the required parameters, or you call them entities. Based on the aggregated usage observed from the videos, the conversational agent can also provide summaries to help novice users get started. For example, the agent might prompt the user you can say, I want large cappuccino. While on the other hand, expert users can directly say the full phrase, such as, I want a large, strong coffee 50-50, to specify the task without going through the dialogue turns. This interaction reduces the time and cognitive effort needed for the blind users to iteratively explore the options on each screen, think about what to do, and then choose at every step. So here the user is talking to the coffee machine agent to specify a task. The user have asked to order hot beverages, mochaccino, and then
Strength from mild, regular, and strong.
Strong.
Select size from small, medium, and large.
Large.
You want large of mochaccino of strength strong, is that correct?
Yes.
Gotcha. I will help you out.
So the user has specified the task. However, the agent is not part of the original interface, so it's not able to complete the task just yet. And next, the iOS application will use these specified parameters through the agent to provide interactive guidance for the blind users to complete the task. So when the user is trying to access the touchscreen interface, StateLens need to re-identify which state the user is currently at in order to provide the corresponding feedback for that screen. The state diagrams can be used to identify states efficiently and robustly. For example, using the user's current fingertip location, the search can be limited to the current and the next expected states observed from the state diagram. So if the user's finger is currently on the first state and second button, then the prioritized search space can be limited to these two states. And if the user's finger moves to the third option, then the expected state also change. In using this strategy, as the number of states increase, the baseline approach to search through all possible states becomes too expensive, as shown in the blue line, and the linearly increase. So StateLens, however, is able to maintain a relatively stable processing time. And finally, to allow risk-free exploration, we then design a set of 3D printed accessories for capacitive touchscreens. So when a blind user is exploring on the screen, the accessories can prevent accidental touches. And to activate a touch, the user can perform a rock down gesture with the finger ring or finger cap. And for the stylus, the user can use another finger to touch the capacitive trace to trigger a touch. And with these components, StateLens users can access a dynamic touchscreen device by following step-by-step directions. And we then perform a series of evaluations. Our technical evaluation with 12 touchscreen devices and over 70,000 video frames showed that StateLens can accurately reconstruct interface diagrams from stationary, handheld, and web usage videos. And our evaluation on the effectiveness of different features also showed that using a combination of screen detection, SERV, and OCR features yielded the best result. Screen detection was especially effective in filtering out irrelevant frames from web videos, for example, the B-rolls or talking heads. OCR, on the other hand, was especially useful in retrieving states with only text changes but minor UI layout changes. And then through a user study with 14 blind participants, we showed that the conversational agent, the iOS application, and the 3D printed accessories collectively enabled blind users to access touchscreen devices that are otherwise inaccessible. Participants were very excited about StateLens and felt that it could help them access other dynamic touchscreens in the future. So participant 6 commented, StateLens gives much more flexibility so that if the machine itself does not have speech, this can cover the instances where you have to interact with the touchscreen. With StateLens, there are more tools to access them. This combination opens up more accessibility. So although solutions like StateLens could enable access post hoc on the substantial legacy of inaccessible devices already in the real world, it is important to note that this is not the ideal solution. Moving forward, it is also important for device manufacturers to embrace accessibility by design. And for future work, although our 3D printed accessories added risk-free exploration to existing capacitive touchscreen devices, in our user study, we discovered issues around holding the accessory in certain angles comfortably and the last centimeter problem to accurately activate the exact button once. So if the screen is cluttered with many buttons, it could still be quite challenging to operate. So to solve this problem, we've started to design hardware proxies that can locate and actuate external touchscreens automatically. So blind users could potentially brush a phone case on the external touchscreen, and then the built-in camera could capture, recognize, and instruct the actuators contacting the external screen to trigger functions at the right place and time. And beyond accessibility for blind people, StateLens could also be beneficial to other users as cognitive assistance. For example, when configuring complicated medical devices, or when interacting with machines in a different language, these guidance can be provided through a visual overlay in augmented reality. These overlays can be in the forms of visual indicators, animated instructions, or simplifications of existing interfaces. And to summarize, StateLens uses a human AI pipeline to make existing dynamic touchscreens accessible for blind people. It relies on videos taken by users to iteratively build up the state diagram and solicit labels from the remote crowd when necessary. And then StateLens rely on machine intelligence to generate the state diagram and the conversational agent to provide interactive guidance to the user. And our technical approach could broadly augment how people interact with the touchscreen interfaces in the real world. And more broadly, StateLens is one of the many human AI systems I've developed in which I investigate hybrid human and AI-powered methods to trade off between the advantages of humans and AI to create systems that are nearly as robust and as flexible as human and nearly as quick and low cost as automated machines. I'm on the job market this year, and I'd love to chat about potential opportunities. And thanks for your attention, and please let me know if you have any questions.